Hello everyone, I am Vivek Srivastava and she is my colleague Faseela. So today we are going to talk about our project Genius and how it helps in application coexistence. So agenda we have is we'll first touch base an overview of the Genius project, what is Genius and its components. Then we'll get into the issues with application coexistence that was faced earlier, and after that, we'll see how Genius is solving those problems, and finally, we'll combine all those pieces together, and at the end, Faseela will be showing a small demo of how this Genius framework can be used. So what is Genius? Genius is an offset one project introduced in ODL boron cycle. By saying that, it's not a new component. There is a history behind Genius. So most of the Genius components are coming from our earlier project VPN service that got introduced in lithium time frame. In beryllium time frame, we matured it further, and that's when we heard about the issues with application coexistence. Different applications like Network and SFC were willing to work together, and they were facing issues, several issues in how these different applications developed independently can work together in one solution. So we noticed that we have such a framework already existing in our VPN service project. And in VPN service, we had several services running on top of these framework components. So we decided to pull out these components and create an independent project so that every other application, ODL application, can use this as a framework and use it for different services or application integration. So by saying that, though this is introduced in last boron cycle, this is a pretty mature code base that is coming from right from the lithium time frame. Then Genius basically provides a generic view of network interfaces. It provides several utilities and services that help in achieving this application coexistence, and that's how this name Genius comes. It's essentially a framework for service integration. So with Genius, you can define network interfaces, and different services can actually bind or subscribe to these interfaces and work together in an interference-free manner. The next advantage of Genius is it decouples the northbound application modules from the southbound plugins or the southbound protocols. So once the network interface is defined in Genius, all the applications and services will only communicate with Genius and referring to those particular logical interfaces. So they are not, application does not need to bother about how those networking interfaces are realized in southbound. That is all hidden in Genius. Genius takes care of how these interfaces are realized in the southbound data plane. Then we also have ability to support multiple southbound renderers. By southbound renderer, we refer to different type of data plane elements or data plane nodes. For example, you can have a virtual switch, or you can have a physical open flow switch, or you can have different devices like TORs, and they are all actually, you can develop a plugin for a specific type of networking element and attach it to the Genius framework, and that will be available for all other applications running on top of Genius. Then it has components or the framework that allows sharing of open flow resources. So what happens, you consider two different applications developed independently. They might be using the same table numbers, and when they are running together, they might be unintentionally programming each other's tables and ruining the data path. So this Genius provides a framework with which you can share the resources across the different application and services so that no one is actually using already used resource like tables and groups. Finally, it's a well-tested production grade software. As I said, like this we are using since the lithium time frame, and in Ericsson we have our solution based on Genius, and we are shipping our solutions to customers based on this Genius. So it has gone a very rigorous cycle of testing. We have done scale testings in different complex scenarios. So it is well-tested and a production grade software. Let's look at the Genius components. So in Genius, we have mainly two types of components. One that actually help in achieving the application coexistence. And then we have several utilities functions that every application uses, and every application or a project writes those applications its own way. And that's how it's a huge duplication of code with every application. So Genius is kind of a common place where you can have a library of those utility functions or those utilities that individual applications can use and utilize their own way. So going by the modules that actually help the coexistence, so we have our interface manager module. So this is the main component of Genius that allows the service integration, where with Genius, this interface manager, you can define different granular logical interfaces. And the interface manager takes care of classification of those logical interfaces. And in data plane, once it classifies a packet belonging to a particular interface, it associates a unique data plane ID for that interface, and the packet travels through the pipeline with that data plane ID that applications can refer to and understand what interface this packet is coming from. Then secondly, it allows a binding of multiple services to these logical ports. So once the logical port is created, different services can bind to these logical ports with specific priorities given. So this interface manager takes care of delivering packets to specific different services based on the priority. So you can have several services bound on top of one particular interface, and a packet entering from that interface will be actually delivered to different services based on the priority. Then again, as I stated, that it has got an ability to plug in a different kind of southbound protocol renderers. So it can work with different type of networking element, like you can have a virtual switches like OVS, or you can have OpenFlow enabled physical switches or TORs, other elements that you can access. So whenever you want to interact with a new network element, you can actually create a specific renderer and plugging that renderer into interface manager, so that the applications that are already integrated with Genius interface manager, they have this southbound element available for access immediately. So because the northbound interface does not change. Then we have our overlay tunnel manager service. So right now, different applications use their own tunneling mechanism. So this overlay tunnel manager provides a generic way where you can create different transport zones, and you can add different tunnel endpoints in that transport zone. Tunnel manager automatically builds a full mesh of tunnels within a transport zone, and these tunnel interfaces are accessible through interface manager. So any application again can bind to these tunnel interfaces and pull packets from these tunnels and use the way they want. Then we have a resource manager framework that actually, if the applications running on top of Genius, for all these applications, the resource manager owns all the resources, and on demand it supplies those resources to different applications. So if every application gets its own set of resources to work with, and that's how they can develop their pipeline and program flows. In the second set of components, we have our ID manager service. So ID manager actually generates a unique cluster-wide unique integer IDs based on a particular key given. So, and these IDs are persisted across the cluster restarts. So why it is useful, like there are different service tags that are used in data plane, and you can generate those tags or IDs from the ID manager, and you can program the data plane with it. And whenever the cluster restarts and the particular application requests an ID with a key, then the same ID is always returned for a particular key. So the key and ID mapping is persisted across the cluster restart, so that you don't need to go and change the data plane whenever the cluster restarts. So all the tags and IDs given by the ID manager are always given in the same manner, the way it was given the first. So whatever the key you specified, for that key, you will get a particular ID value every time. Then we have MDSAL utils module. The MDSAL util modules basically, it's a utility. It provides a set of APIs, Java-based APIs to access and talk to MDSAL. So today, every application that is using MDSAL, you want to read and write, and every module writes some functions to access, or wrapper function to MDSAL data stores. So this MDSAL utils provides a common place where all these methods are available. So every application can get use these APIs from MDSAL util. Apart from that, it also has an OpenFlow programmer module. So you get a very simple API to define your flows, and you give it to MDSAL. MDSAL translates into actual MDSAL transactions and writes to the plugin data stores. Then we have a FCAS framework and application. This is a work in progress. So this FCAS application actually generates various alarms and counters from different Genius modules. And FCAS framework actually enables collectively fetches these information and prepares a block of history data, and that any application from the top can access these data from FCAS framework. So these are the main components. Like we have some other components also minor, like we have aliveness monitor for tunnels. So these I have not mentioned here. Let's look into the application coexistence. What is application coexistence, and what challenges are there with the application coexistence? So main challenges with the application coexistence, I touched upon these points earlier also. So it is mainly the partitioning of OpenFlow resources. I was saying that if the two applications are developed independently, they can actually use the same resource in their pipeline. And when these two services run together, they might be actually writing to each other tables unknowingly and creating problems there. So that was the problem earlier, because when these discussions about the application coexistence started, there were mature applications who were well-defined using their resources with specific IDs, and those resources were used by different applications. And when they run together, they found that, like, okay, we are using the same tables, and each table they are referring for a different purpose. So this was a problem that identified earlier, and as I was showing, our resource manager is pretty useful in solving this problem, where resource manager actually owns all these resources and provide these resources to individual application on the request. So whenever a new application is started, it will go and first request a set of resources from resource manager, and that will be returned. Then we had the issue of ingress multiplexing. That is the table 0 problem. So you see, the table 0 is the table where the ingress, all the packet enter, and each application wants to get packets from ingress and process its own way. And for that, they had to program a table 0 in their own fashion. So for the same packet, different applications are writing table 0, and this resulting in a conflicting rules and creating problem. So there was a need for a generic view of, a common view of this networking interface or ingress flows that can be identified and used by different services in a generic manner. Then most of the applications were writing mainly based on the OpenFlow port based. So in table 0, you identify which port, OpenFlow port it is coming in, and then you apply a specific service onto it. Then there was a need for defining further granular interfaces that can actually enable different applications to use a different level of granularity on which they can apply their services. Then again, we had the issue of that, like we want to apply two different services on the same interface. So you can imagine, like from one particular port, a packet coming in, and two different applications are interested in the same packet. So who will actually get this packet first, and who will process this packet first? This was the problem there. Then there was issues with multi-tenancy. When you apply services, how you will isolate different tenants or different components. So there was a need for specifying the service-specific tagging to these interfaces. And this was mainly related with the table 0. And our interface manager is exactly solving these problems by defining generic interfaces and binding multiple services to these interfaces. Then again, the third main problem with application coexistence we saw was like integration or cooperation between these two different applications. Because say if one application views a particular network interface in a different manner, and a different other application views the interface, defines the interface in a different manner, they cannot actually agree on working together in a common way. So there was actually no common interface through which they can define interfaces to get these services enabled on top of these interfaces. Then the issues were, the second issue was like transfer of packet. As I said, like say consider two different applications are having their own pipelines, and say they agree that first the packet is delivered to first service, and then it has to be delivered to the second service. So which is the entry point of the second service and where the packet will be sent next. So these were the issues during the application coexistence discussions we discovered during the Beryllium time frame, and we came up with our Genius solution. So let's see how Genius works. So in Genius, if you see, the ingress and egress is owned by the interface manager service. So interface manager basically provides an API, Yang-based API, to define different interfaces. You can define interfaces in interface manager, and with those interface definitions, so you can provide the classification parameters for a particular interface, and based on the classification parameters, interface managers programs this table 0 and maybe additional tables to achieve further granularity of those interfaces. Then we have our service dispatcher table. The service dispatcher table is actually the one who is arbitrating packets across different service pipelines. So what happens that when a service is bind to a particular interface, the interface manager adds the corresponding entry in service dispatcher table for that particular service. And if you have, say, 2, 3, 4 services bind to the same interface, you will have as many entries in this dispatcher table. So what happens, and these entries are based on the priorities that are predefined with our service bind mechanism. So when the packet enters the table 0, the interface manager rules classify the packet and identify that this packet belongs to this interface. It actually associates a corresponding data plane ID with the packet. It actually the interface ID is associated is added to the metadata of the packet, and the packet is sent to the dispatcher table. Dispatcher table further looks into like what interface it matches with that interface ID and the service priority, and see like which service is the first where the packet is to be delivered, and then dispatcher table delivers this packet to the service pipeline. So the service pipeline, or the first service pipeline, may consume the packet. Consuming mean it may drop that packet, or it may forward the packet to the egress or the egress interface. So if that happens, the journey ends here. Packet goes to the egress dispatcher table, and from there on it goes to the egress ports. But if the packet is not consumed by the service, the packet is actually resubmitted back to the dispatcher table. Dispatcher table again picks the next service priority service and delivers the packet to the next service pipeline. So we'll see in the following slide how this is achieved. After these packets are actually come to the egress, we have the similar service binding mechanism at the egress. So as we can bind services to the ingress interfaces, we can bind services at the egress of an interface. So consider that service 1 is doing normal L3 forwarding, and at the end of this service pipeline, you identify the egress interface. Again, these are all applications are looking these ports as interfaces, logical entities. Once the egress interface is identified, the packet goes to the egress dispatcher table, and the specific egress services bound to this interface will be again applied on that packet. And finally, the packet is sent to the interface manager egress groups. Egress groups are like basically if there is some packet rewrite at the egress you want to do, that is actually done here. You can apply encapsulation headers, and finally once that is done, the packet is sent out on the port. Now moving to the next, how it works. So we'll go touch a bit on how these components work together. So interface manager, I have spoken a lot about interface manager. So with interface manager, you can define generic network interfaces, providing specific classification parameters for that interface. And once the interfaces are defined, interface manager actually programs the table 0 with specific rules to identify or classify that particular packet belonging to the interface. And it associates a data plane ID or interface ID with each packet once it is classified belonging to a particular interface. Then we have our service binding mechanism. So we have Yang-based API with which you can different application can bind services on a particular interface, giving specific priorities. And once this is programmed, the interface manager programs the dispatcher tables accordingly, and delivers the packets. So the important thing to notice here is like at the time of binding the service, the specific service binding rules are provided by the services themselves. So we are allowing the services to provide any open flow rule or action that we can apply on the packet once the packet is delivered to that particular service. So, but normally these service binding actions are generally to put some service specific tag in metadata and a go-to table to pull the packet to a specific service table pipeline. And the third is, like as I stated, that this interface manager hides the southbound from the application or the services. Services only see and operate on the well-defined interfaces, and how these interfaces are realized in southbound or the data plane, that is all handled by the interface manager. So this is here we define the interfaces. So interface manager is a Yang-based API that is based on a standard IETF interfaces data model, and we have additional augmentations added to further classify granular interfaces on top of one particular OF port. So you can see here we have different type of interfaces. So the black ones you can see, these are coming from the standard IETF interfaces data model, and the blue ones are the one augmentation that we have added to realize different type of interfaces. So one important augmentation that here you can see is the parent refs that we have added. So with the parent refs, you can create a hierarchy of interfaces. So on top of the hierarchy, you can have one OF port getting all the packets, and on that OF port, you can create a trunk interface, and then you can define further granular interfaces with different VLAN IDs. So one interface is classified with a particular OF port and the VLAN ID, and different application can bind services to these specific granular interfaces. So we have several different type of interfaces right now available. It is well extensible. You can add different type of interfaces and add augmentations to it, and create new different type of interfaces. So right now we have our VLAN, L2 VLAN interfaces. So L2 VLAN is actually kind of misnomer, because with L2 VLAN we are referring to any L2 port. So when we don't have any VLANs also, we create an L2 VLAN port and L2 VLAN interface actually, and bind services to it. In the same way, we have our tunnel interfaces. So you can create different tunnel interfaces. I said like our tunnel management service. So the tunnel management service is based on interface manager. So actually the tunnel interfaces are created by the interface manager, which is actually managed by our overlay tunnel manager. We'll see in further slides. So you can have right now, we have VXLAN or GRE tunnels, or we have other tunnels also. Let's look into the service bindings. So again, the service bindings can be defined with Yang-based API. We have a Yang-based API with which you can actually bind services to a particular interface, and while binding services to an interface, the different service modules provide these main attributes. So the important ones are the service priority and the service info. So service priority tells like in order in which the packet is to be delivered to a particular service, and the service info is the instructions that are applied before the packet is actually delivered to the particular service pipeline. So these are all supplied by the specific applications who are binding these services. So what happens and how it actually works? So as I said, when the service is bind, the service dispatcher table is programmed. So when the interface is created, the table 0 is programmed with the classification parameters for that particular interface. Once the packet matches with a particular classification rule for a particular interface, corresponding interface index and a service index is added to the metadata of the packet, and the packet is sent next to the dispatcher table. This line is again, actually the packet is sent directly to the dispatcher table, and in dispatcher table we have individual rules for different services, and you can see the matches on service index, and each service index refers to a different service. So when the packet enters the dispatcher table, it will first hit the SI0, that is referring to the first service, and after matching this rule, the service-specific rules are applied, along with the service index is modified to be the next services index. And then the packet is transferred to the next service. When this particular service actually consumes this packet and it forwards it, the story ends there, but otherwise it sends it back to the dispatcher table. Dispatcher table, now the packet will be having the next service index, and it will match to the next service rule, and the packet will be forwarded to next service in the same way. So this follows with the different services, so you can apply different services, and the packet will traverse each service in order, and finally it will be sent out of the interface. So we have this. So going to touching the resource manager. So before resource manager, we have our ID manager service that I specified, that actually generates unique integer IDs. So the resource manager is actually based on this ID manager service. So idea is to have a common resource pool managed by ID manager for different OpenFlow resources like tables, groups, and meters, and all the application will request for these resources from the resource manager. Resource manager will provide the set of resources to different applications. So how resource manager works? So a resource manager, we have system property or resource pool config that actually with resource pool config we can define like the total available resources. So for example, you can say the table pool, we can say that from 10 to 200 are the available tables, because you see the interface manager reserves some of the initial tables, and that is not available for other applications to use. So the table pool actually has all the available tables or the resources that applications can use. So when the resource manager starts, actually it reads the table resource pool config and creates those pools in ID manager. And further on, whenever an application requests for a particular resource or a set of resources, resource manager again queries the ID manager and get those resources and return to the applications. So again, as the nature of ID manager, all these mappings are actually persistent across the restart. So say when the controller restarts again, it will again give the same key and get the same set of the resources every time. Then we have our tunnel manager. So as is specified, like with our tunnel manager, you can define different transport zones, and you can add tunnel endpoints in these transport zones. And once the tunnel endpoints are added in a transport zone, this tunnel manager dynamically creates a full mesh of tunnels between these endpoints in a particular transport zone. And so if you want to have isolated different sets of transport meshes, you can create several transport zones and as per your need. Also, additionally, we have APIs to add external endpoints. So external endpoints like external entities like TOR or DC gateways. So in this case, you don't have control over these external devices. So you can have only unidirectional tunnel towards these devices. So that's why it's a separate API where you can say that you want a unidirectional tunnel to these external entities, and you add these external entity as an external endpoint, and this tunnel manager automatically builds tunnels to those external endpoints. So we have several tunnel types currently supported. So you can see VXLAN GRE or VXLAN GP or MPLS over GRE tunnels you can create and manage. So once you create a tunnel, it is available as an interface, and you can bind services in the same way as you bind services to any OF port. We also support the tunnel monitoring service. The tunnel monitoring, we have our BFD monitoring and LLDP also, since LLDP monitoring actually involves the controller also, so it's not that is scalable. So mostly we are using BFD. And on the basis of with this tunnel monitoring events, this tunnel state is changed, or tunnel up down events are generated by tunnel manager, and different services or application could subscribe to these tunnel up down events and take appropriate actions. So a little bit of southbound renderers. So the interface manager design is kind of kept modular with we have two separate sections. You can see we have listeners and renderers. So listeners basically actually access the interface manager data stores, and whenever a new interface is created, the interface config listener will listen to those interface creations. Same goes with the service binding. So this listener module is isolated from the southbound renderers, and you can have you can attach different southbound renderers. Right now we have our southbound renderer for OVS that actually uses OpenFlow and OVSDB plugin, and then we have our one hardware VTAP renderer that actually we are using to create tunnels or access tunnels on the Tor devices. So but this is not limited. I mean, as I said, if there is a new kind of element in the data plane that we want to access through interface manager, we can add a new renderer here for that specific. So that will not change the upper part. It's only the lower, the renderer part is added, and these listeners will actually access these renders through a generic interface. Okay, now putting it together. So again, is this the same initial picture? Now I'll hand over to my colleague Faseela. She will give a short demo how you can create interfaces and bind services to it, and then we'll finish this session. Thank you.
Hello everyone. So Vivek already explained this diagram. So I'll be doing a simple demo and explaining the details of this pipeline and how to use it to achieve application coexistence. I think you guys are almost clear with this pipeline. So we have an ingress table, that is the table 0, and then a dispatcher table, and then various ingress service pipelines, and then the egress dispatcher table, and finally the egress group. So currently, one of the active users for this ODL Genius framework is OpenDaylight network feature. So they are achieving application coexistence using the Genius model. So this is the whole pipeline for the network VPN service feature. As you can see, the table 0, table 36, table 38, and table 220 are owned by Genius. And the various services of network which achieves application coexistence using Genius are, you can see that there is a DHCP service, and then ACL service, both ingress and egress, and then their L2 VPN, L3 VPN, and IPv6 they currently added. So all these applications are able to program the service pipeline very easily and seamlessly by using the Genius framework. Now coming to the demo, I have a very simple setup so that it's very easy to understand how we can achieve this application coexistence. I just have one OVS running on a VM, just 2 ports on this same OVS. Okay. So what I'm going to do is I'll use this Genius framework to configure the service pipeline and show that how they're able to communicate with each other. So the various modules of Genius which will be internally utilized for this are interface manager, and then resource manager, MDSAL utils, like that. So my controller is already running. ODL Genius UI is the feature you can use for the same thing. This comes automatically, it will get installed if you guys are using this network VPN service feature, or if somebody wants to use Genius separately, they can use ODL Genius UI feature. We have a set of CSIT in place for the same thing, and it's completely like stable, and that's already part of the Boron release without the experimenter label. So it's more or less stable. You can easily use it. Okay, so I have a Mininet VM here. Somehow I'm not able to maximize this. Okay. So I just started the Mininet VM. So what I have is one switch S2 and two hosts H3 and H4 connected to this switch. As you can see now, this script creates two ports, S2 ETH1 and S2 ETH2 on this bridge S2 of OVS. So now what I'm going to do is through the interface manager module of Genius, I'll configure two interfaces, L2 VLAN interfaces on top of these two ports. So currently I don't have any script, I'm just using directly the Postman and directly configuring it. So if you see, I have given a unique interface name and then configuring the interfaces. This step will program the ingress and egress flows for the various interfaces configured. Now maybe okay, so it's coming like I'm not able to maximize this. Okay, so maybe I'll just explain it. I'm finding it difficulty to maximize this. So there are two interfaces configured since we had two ports. The first one, so one entry is configured in table 0. Since its port is ingress port is 1, you're seeing a match on ingress port 1 and there is a metadata written. And it says go to table 17. Table 17 is the ingress dispatcher table. So if you see the metadata, we use ID manager to generate a unique ID called lport tag for the interface. So this is going to be unique per interface configured using this system. Similarly, there is one more table 0 entry for the next interface, again which says go to table 17. And there are two entries in table 20, which is basically the egress side of the same thing. So ingress and egress part is programmed when we say configure interfaces. Now we have the bind service step. Currently I'm binding one single service on these two interfaces. So once this is done, you will see the ingress dispatcher table entries programmed. Okay. So if you see, Vivek already explained how to configure, what are the various attributes used for configuring interfaces. You need to give the interface name and you have to tell whether this is going to be an ingress service or egress service and various details of the service. Like what is the priority? Main thing is the service priority. So if you have multiple services bound on the same interface, interface manager takes care of dispatching the packets between the services based on their priority. Right now I've configured only one interface and actually more instructions can also be passed along with this JSON. If before going to an application pipeline, if you want to set some service tag in the packet, that also can be done in the same way. So now I have bound one service. Now you can see for both interfaces, two entries have come in table 17, which matches on the metadata, that is the lport tag which was set in table 0, and it sets a different metadata. Basically, this is same lport tag plus a service priority. So if this is the highest priority service, you will see the first 3 bits will match accordingly, and more services are there means you will see different service IDs there. And right now what I've done is I have mentioned that my table pipeline starts at table 66. This was given when I do bind service. So in table 17 you'll see that write this metadata and then go to table 66. Now since I don't have any service pipeline, what I've done is I've created a dummy service which simply says go to egress dispatcher table. usually we will have some well-defined services like L2 VLAN, DHCP or L3 VPN. For example, if you take L3 VPN, it will tell match on some destination IP, go to the corresponding egress interface, something like that. Here, just for a demo purpose, I've just configured a simple service which says set the egress interface tag and then go to egress dispatcher table. Once the whole pipeline is programmed, you can see that these two hosts are able to ping each other. For example, if you delete the service pipeline, you can see that it will not ping. Create it back. So it's just a simple demo. So just wanted to show that the ingress and egress pipelines and various IDs being used are uniquely handled by the Genius project and using the various modules. If you guys have more doubts on how to use it extensively by binding multiple services and how does it work, please feel free to come to any one of us.
We will be there. We have several sessions at the DDF also, so you guys can join there. And we will be mostly available at our Ericsson booth also. So if any questions, you guys can drop in and we can discuss further. Right?
Okay, so currently we have, there were discussions on how to integrate SFC, GBP and also if there are more applications which are interested to integrate, we will be more than happy to help you. So please feel free to reach us. Okay, thank you.
Thank you. Thank you.